Good morning. We are from SUS Embedded and the project title name is called Integration of a Polymorphic Sensor for the Pulse Measurement in a Zigbee Medical Network. In this project we are using an ARM processor. It's a 32-bit processor which comes under LPC2148, and we are using some sensors called an heartbeat sensor, and it's a pulse sensor, IR photodiode based, and here we are using an LM35 temperature sensor, precious temperature sensor, minus 55 degrees centigrade to 150 degrees centigrade, and the data should be displayed onto the 16x2 LCD display. And we are using an Zigbee Tarang F4 module. It comes under 30-meter distance, and the receiver end we are using an LabVIEW, which comes under an body plot and the waveform of the heartbeat plot, and we are using an thermometer which will display the temperature, and we are using an LabVIEW. So all the data should be updated information in the form of graphical form. So we are using the receiver section of PC, LabVIEW, and the Zigbee. It's were connected to the Max 232 of the module. So this is an receiver section, and which is an transmitter section. So the total, this was the body, we are connected to the body. So here we are taking the first of the transformer, which we will act as a the power supply section to the microcontroller board. Otherwise we will go for the battery also. So our continuous purpose, we are going for the transformer, 0 to 9 volts transformer. It's an 230 input step down transformer, 9 volts output AC, and 500 milliamps current, which will give it to the bridge rectifier. So in front of the bridge rectifier, here we are using in 4 diodes, 1 and 4007 diode. So the main purpose of this diode is which we are giving the AC, it is converted into the pulse rated DC. It's not pure DC. So we are converting here, we are taking in 1000 microfarad by 25 volts electrolytic capacitor. This capacitor will convert, it will capture the AC and it blocks the DC. So the main purpose means we have to eliminate the ripples. So the bridge rectifier, it converts the DC, so there is a fluctuated DC. So we have to take that AC ripples. So this is in the filtering the capacitor. Here we are using an LM7805 regulator. This regulator will convert 9 volts AC to 5 volts DC. Why we are taking the 5 volts means all the components which we are using. So let us assume that here the LCD, it is working under 5 volts. Max 232, it is working under 5 volts. Remaining and the heartbeat sensor, it is working under 5 volts. And the remaining all we are in the form of 3.3. So that's why here we have another regulator. That regulator is called LM1117 fixed 3.3 volts regulator is there, which converts 5 volts to 3.3 volts. Actually we are taking the 9 volts, we are converting into the 5 volts. 5 volts for the LCD, Max 232 and the heartbeat. And after that our remaining components which we are using, and LM1117, it is working under fixed 3.3 volts for the ARM processor and the Zigbee module and the temperature sensor. These are all working under 3.3. So that's why in our board we have a 5 volts power supply as well as 3.3 volts power supply. So we used one board. This is an development board which comes under all the peripherals like power supply section, Zigbee module, and the RTC, USB, LEDs, and robot purpose. So this development board which comes under all the peripherals. But our main motto of our project is we have to communicate some Zigbee to the wireless, and we have to take the data from the sensors of the LM35. Here we have a LM35 block is there. It's a temperature block. This block, this is an ADC, analog to digital conversion block. This block is connected to the P0 of 20th pin of ARM processor, and we have another, that is an hot bit, which connected to the switch of P0. P1.18 is connected to the switch, and P1.7 is connected to the hot bit receiving. So that's way our development board will communicate more number of devices at a time. So this development board, it's an ARM based development board, LPC2148, ARM 7 advanced RISC machine, LPC, low power consumption. 21 is the version, 48 is the IC number. So 48 consists of some peripherals. So our IC having 64 pin IC, total 2 port 0 and port 1. Port 0 consists of port 0.02, port 0.31, and remaining port 1 consists of port 1.16 to port 1.31. So total it will execute 16-bit architecture as well as 32-bit architecture. At a time it can send 32-bit and the 16-bit. So port 0 32, port 1 16-bit. And here in our project we are using port 0 for the LCD and port 0 for period 28 for the temperature, port 0.0, 0.1 for the Zigbee, port 1 for the hot bit. So in our project we are using at least 6 pins, 2 pin, 8 pins, 1 pin, 9 pin, 1 pin, 10. So almost in our total 48 input output. So port 0 32 pin, port 1 16 pin, total 48 input output. In our project we are using only 10 pins, remaining 32 pins are wastage. So that's why we will go for the more number of applications we can go for this project, and it will execute 1 microsecond delay, means it will execute fast 32-bit. So in our project we are using an ARM processor. So here this is an crystal in 12 MHz crystal. This is the heart of the circuit for the microcontroller. To generate the clock pulses to the internal CPU, it will run the program. So in our board we have one ISP switch and one reset switch, and LCD side switch is called the reset switch. After that switch is called the ISP. When we want to dump the program onto the microcontroller using an UART0, we can dump the program. Using an flash magic, we have to press the ISP continuously and press and release the reset. The program will be dumped the microcontroller. Means using an flash magic software we can dump using an RS-232 cable which is connected to the UART0. UART0 in LPC2148 it was configured as an ISP. In system programming, means this IC is an fixed IC. It is a not removable IC. We can dump the program for 1 lakh times to test it. It's an ISP, though internally the IC which was programmed as an ISP in system programming. That's why this switch is called ISP and the remaining switch is called the reset. When we want to dump it, press and release the reset, the program will dump it onto the microcontroller. When the program is dumped, we have to press and release the reset. The program is continuously in the form of executable format. So ARM processor UART0, UART1. UART1 we are not using, only UART0 which was configured as an Zigbee. So when you are dumping, it should be removable. When you are executing, it should be connected. Okay, so here we are using an Zigbee. It comes under 9600 baud rate, 2.4 GHz frequency, up to 30 meters Zigbee, point-to-point network. It will send the data. Okay, you can go for the data sheet. And here we are using an LM358 based operational amplifier which was connected to the hot bit. So internally there is an IR transmitter and IR receiver is there. You can observe on my video which was Okay, the light will be shows. That light shows means IR is passing. When the IR is passing, you can put it your finger into that high low pulses. When the high low pulses, the LM358 will configured as an high low. The amplify the signal. It is giving in the form of ADC, and the microcontroller will take the data and it should be display the data. And here with the display, here we are using a 16x2 display. It's a character display. Whatever the process is going on to the controller, that should be displayed onto the LCD. So nothing but it's a monitoring unit, whether the data is perfectly loading or not. If it is getting that some garbage, we have to restart it. And here we are using a port P0.28, which was connected to the LM35 temperature sensor, precious temperature sensor, and we are taking the first, it is getting the data in the form of degree. 10 millivolt equal to 1 degree, and 30 millivolts 300 millivolts is called 30 degree. So that's way we are converting into the Fahrenheit. That Fahrenheit formula is F actual value degree into 5 into degree into 9 by 5 plus 32. It will display the Fahrenheit value. So whatever the data we are getting, that was giving to the another Zigbee module, same to same, which was peer-to-peer network of the ID address. So which was uploaded to our data. Means here we have a LabVIEW software, which the LabVIEW software, which we will get the data in the form of plotting. Okay, stop. Okay, so amplitude, so the temperature 84 it is coming. So which we are giving my body, okay, 86, and my hand and my another finger. So it is giving the plot, and you can observe the read buffer, and you can observe the thermometer, which will give you the thermometer plotting. You can increase the temperature, press it, and you can observe the heartbeat. That heartbeat will also displace, and the temperature will also displace. According to the LabVIEW, we will go for the multiple combinations and multiple receivings. Okay, we will give you the indicator also. Indicator will indicate the heartbeat, and it will give you the floating. Means this is a sine wave graph which was designed, and a read buffer will continuously display the reading value. Press it, press continuously. Okay, heartbeat it was displayed, heartbeat 65, heartbeat 69, heartbeat 69, temperature. So all the values which will displays in the form of floating value, floating graph. Okay, so we will go for the more number of devices to connect at the LabVIEW also. So the main motto, we have to monitor the data of the patient in the form of the graphical representation. So thanking you. If there is any doubt, let me know to SVS Embedded.